Hi, good evening. Welcome back to this webinar. Before we start, our CEO, Dr. Emil Somek, will like to share something very special and unique before I start over the session. Emil, I've made you the presenter, so you can share your screen and start.
Hello, everybody. I'm glad to have joined this last webinar on this year for this great version SolidCAM 2021. I'm sure you will enjoy Amod's presentation. Before we start, I just want to remind everybody again about a major manufacturing marketplace that we are launching called Solid Metal. It's an application, website in the internet where we connect buyers of CNC jobs with manufacturers all over the world. Obviously, the manufacturers are you, our customers who have your CNC machine shops, and you want to offer your services to the buyers who want to give you the service. And we will have here customers, SolidCAM customers from all over the world who can register their information in this platform. So if you are a manufacturer, which means a CNC machine shop, so you put all the information about your CNC machines and about the type of CNC work that you want to do. And if you are a buyer, you could post the CNC job that you want to be done by a manufacturer, and then this link happens between both the manufacturer and the buyer. But to be able, as a SolidCAM customer, to put your information in this platform, you must be on valid subscription. Now also, you must have our iMachining module, because if we are going to recommend you to all the buyers all over the world, we must make sure that you have the best tools. Basically, our latest version with all these capabilities, latest SolidCAM version, and also you will have iMachining that saves tons of time and tool costs. So if you want to be included in this platform, please make sure to be on subscription and also get the iMachining module. And as you know, we have now very special conditions for you to do this till the end of the year, where it is very good conditions, and you can also get the iMachining modules at half cost till the end of the year. So rush and make your subscription and get your iMachining module. So basically, as I said, all the buyers will post their CNC job work here, and we could get codes and choose of the codes. So are there any charges? Not at all. This is service we give free of charge to all our customers worldwide, and obviously to the buyers who want to give them CNC jobs. And we will market this application strongly everywhere, so that people who want to give CNC jobs will find it. That's our job, to market it very heavily worldwide. So this marketplace provides a networking capability between buyers and manufacturers. And by putting your data as a manufacturer, you can get discovered by a lot of buyers worldwide. So it's more or less ready. What we are going to launch it in the next couple of days. And I think it will be very useful to you as a SolidCAM customers. Enjoy. Amod, continue.
Thank you, Emil. I'll make myself the presenter. Can you make me the presenter, Emil?
Okay, let me see.
Okay, I think I have it here. Yeah, I got it.
Okay.
Right. Thank you very much, Emil. I got it. Okay, so after that short introduction about the solid workplace or solid metal workplace, let's move on to what's new in SolidCAM 2021. So I'm going to start my presentation. So SolidCAM 2021 has been in works for more than last couple of years. So it's been a long journey, and we released it only somewhere in mid this year. So it's been a pretty long journey for us. Uh, so if I go ahead, so historically, what we have seen is that SolidCAM 2021 is our best ever version. Looking at the amount of work that has gone behind the product, looking at the features that have gone into the product, and the amount of testing and the QA that has been done on this, we feel that this is our best ever version. Of course, we can't predict our future. 2022 will be the next best version. It has a powerful new tool table. We completely revamped our tool table because our entire focus, or you could say the maximum focus for 2021, was on advanced Milton and Swiss type, and these two technologies need a much more or a different kind of a tool table that suits the definition of tools in these two machines. So we have completely revamped the tool table to support what we call as assemblies of tools, multi-bodies assemblies of the tools. And this has been uh, developed keeping in mind the advanced Milton and Swiss type customers. We developed a completely new SolidCAM simulator. This is This has got the look and feel again of SolidWorks. It can work either inside the SolidWorks environment, or you could just pull it out. If you're working on two different monitors, you can take the simulation and put it on the second monitor and continue working on your part. So the simulation happens simultaneously without the fact that it will disturb you or you have to stop your work to see the simulation. The simulation can continue. We have some advanced functionalities in our additional functionalities in advanced Milton and Swiss type. And apart from developing quite a lot of things for tool table and Milton and Swiss type, we continued our focus and our synergies to develop functionalities in 2.5D milling, in 3D milling, that is HSR, Turbo HSM, and HSM, and also the Sim5X capabilities. We have done quite a lot of improvements also in this area, and it's not that we have just done only the advanced mill type tool table and the new simulator, but a lot of things have also gone into making new features into these areas. Okay, I'm going to talk about tool table, but I will not run the entire presentation because it's highly technical, but I'm going to show you the features, salient features, and also I will jump directly into the software to show you how the new tool table looks like. So we have got a completely new tool table, which does the definition of the tool as an assembly and not as a single solid body. Earlier, this used to happen. Also, we could do assemblies, but it was a slightly more tedious and a more tricky affair to handle assemblies, especially tool assemblies for Milton and Swiss type. Also, for milling, for customers who are using the right angle head, it was a bit difficult to define these kind of assemblies in 2020 version or 2019. In 2021, this is completely revamped, and we have got a completely new tool table, which works like as if you're building an assembly of the components. How it used look, for example, the classic tool table look that we had in 2020 used to look something like this. And now we have the new tool table, which is a unified tool library system that facilitates better tool management, and it provides major enhancements in the tool definition functionality. You can manage the tool items available for use for specific CAM paths and in accordance with the CNC machine chosen. So now what you can do basically is you can create a tool table or tool library specific to a CNC machine. And when you call that CNC machine into your part definition, the tool library also gets loaded along with it. This is so much important for Swiss type customers who have their tools set according to tool numbers, and that doesn't change. Generally, once they set the tools, they don't change. So they would like to have the same tool type in the same tool type, tool number. So you can actually set the entire tool library specific to the CNC machine, and whenever you call the CNC machine, you also get those tools along with the tool numbers that were set while you were defining them. So what I'm going to do now is I'm going to quickly run into the software because it's a pretty interesting thing that we have in the new tool table.
Hello.
Hi, Emil.
Hi.
Sorry, that was a small disturbance. So what I'm going to show you is, first of all, I'm going to define a very simple milling tool and show you how the components are assembled in the new tool table. And then I'm going to show you another very interesting aspect of the tool table on how you can actually import from different tool manufacturers tool tables or tools directly into SolidCAM along with their 3D models. Okay, so let's start quickly. I'll go to my part. So instead of tool table or tool library, we have something called as toolkit. We've called this toolkit because it provides a kit to create assemblies of your tools and holders and multi-components. Basically, you can assemble the entire right angle head as a tool and call that tool in your library. So that's the reason why we have called it as toolkit. Sorry. So this is how my classic tool, or rather my new tool table looks like. So if I want to add a new tool, for example, I want to add an end mill, I can just double click the end mill here, or I can just drag it and drop it in my library here. And this is how my tool comes up. So I have got the tool library here, or rather the tool component here, where I have got the topology. So I enter the dimensions that is needed. 10 diameter, cutting length, let's say it's 25, shoulder is 35, total length is 80, out of holder is 40, number of flutes 4. Now I can add on top of this, depending on what machine I'm using. For example, let's say I'm using a DMG 65 monoblock. Okay, in such cases, I can go into the adapter or the holder and call for an HSK63 adapter. So I can just take the HSK63 and drop it into the holder area. So you can see that now we have an HSK63 holder, and I can put on the side the how the tool is looking like. I can get a preview straight away. After we add the adapter, okay, after we add the adapter, I can add what is my holder. So I'm going to put from the library that we have, HSK63 shrink fit 10 by 50. So I just take it and drop it into the area here, and my assembly is complete. So now I have the component on top, which is my holder. I have the adapter, and I have the tool itself here. So in the similar way, I can define any kind of tool, any kind of any type, basically, whether it's a bull nose, ball nose, or a flattened mill, or a face mill cutter, or even in turning, I can define whether it's a external turning, internal turning, grooving, threading. So you can define all these cutters as they are as an assembly. So each of them have got their joints. So we have got a joint coordinate system. You can see that my end mill is connected to the adapter here. The adapter is connected to the holder here. And this is my spindle coordinate system. So this is where my spindle is going to rest. So this is how we create assemblies inside SolidCAM's toolkit. Now let's do a very interesting operation, okay? Let's say I have got my tool and I work with ISCAR, okay? So I'm working with ISCAR. So what I will do is I'll open my browser and I open the ISCAR catalog library, what they call as a catalog library. And I would like to have, or I would like to get from ISCAR a face milling tool. So I'll click on milling. And when I click on milling, I get the features or type of operations that you can perform with their tools. So I would like to do the facing operation. And then once I click on facing, ISCAR tells me basically which are all the possible options that you can use for working in with their cutters. So I'm going to pick this cutter, HM90. And with an HM90, it gives me three options here. So depending on which diameter I would like to use, I can select the option. I would like to use a 32 diameter face mill. So I'm going to select the 32 diameter face mill. So I'm now in my tool, and you can see that here, ISCAR gives me a possibility to have a detailed view of the tool. Okay, so I have got the tool, but without the insert. So if this is my final tool that I'm going to use, I'll click on Add to Assembly. Okay, perfect. So when I click on Add to Assembly, you can see that it has got the holder. Now there are two items that are still missing. Now this is very smart. So I'll click on Add Holder because the holder is missing yet. So I'll click on Add Holder. And again, it shows me only those holders that are suitable for this particular tool. So I will use the BT type holder here. So I'm going to select the first one, BT 40 SEM 16 by 60. And I'll add this to the assembly. Okay, this is what is the holder that I'm going to look for. I'm going to the detailed view. Detailed view sometimes can take some time to load up because if it has more features, then it'll take some time to show up on the screen. So I'll add this to the assembly. My assembly is now updated. I'm getting the holder as well as the tool body. What remains now is the insert. So I'll click on the insert. And again, ISCAR shows me all the possible inserts for the tool body that I've just selected. So I'm going to use, let's say, APKT 1003 PDR-HM. This is the general purpose insert. So I'm going to select this insert. And there's only one possibility. Of course, there are grades here. Basically, if I click on the grades, I'll only get the VC and the cutting speed. Otherwise, the geometry, I just click on this. Okay, so I've got several of them. I'm just going to pick the first one, and I'll add this to the assembly. Right, so my assembly is done. Of course, like I said, for the detailed image to appear, it will take some time because it needs to load everything. I'm not going to wait for it. I'm simply going to click this button and download the assembly, which is basically going to give me the depending on the speed, depending on the components that are there in the part. So again, here I'm going to save it. So like I said, it takes some time for it to show the detailed view. So I've done that. I'm going to open the part, cut this part, and go here, go into the SCAR tools, and I'm going to make a new folder here. I'll say new webinar. Okay, and here I'll make another subfolder. I'll say milling, and I'll just paste this here and just rename this fellow. Say face mill 32 die. So it's a step file that I've got. It's more than enough. I'm just going to close this for a moment. Sorry. I'll just close this for a moment, and I'll import the step file that I just got from ISCAR. Remember that these steps are common. These steps are common, and it doesn't matter where or which particular tool manufacturer you're using. Once you get this this particular file, rest all steps are common to us. So I'm going to start again and or rather open the CAM part. I'll open the toolkit. Okay. So I'll add an endmill here and minimize the toolkit. Go to my window and I'll open my face mill diap or the face mill tool basically, and I'll click here on import tool assembly from CAD. Now, before I do that, I have to do a couple of steps, okay? And this step basically is needed because of orientation difference. So I will have to add, or what I'm going to do here is let's create a plane at this point, somewhere here. Yeah, oh, sorry, not the edge. Okay, so I'll just create a sketch here. Okay, this is just for me to create a coordinate system. Oh, this is horizontal. Oh, vertical, sorry. Okay, another line on this side just for me to put the y-axis. Okay, this is done. So I'll create a reference geometry. I'll say this is my coordinate system. Delete. This is my origin. Sorry. Okay, and this is my x-axis. And this is my y. Okay, so z-axis is in that way. I'll accept this. I'll save this file. Let's not put it here. I would like to put it back into the SCAR tools, new webinar milling. Save it. Okay, so this is done. I'm now going to open my toolkit, and I'll click on import tool assembly from CAD. I'll say okay, because this is my active window. So it's now asking me, what do you want this tool to be? What do you want this tool to be? There's a question that the UCS should be in the model. Actually, Doran, I checked it before. The UCS is in a different plane, so I don't get it the way exactly I want it. So I have to create a new UCS. So I'm going to generate this as a milling tool. So there you have. It creates this tool inside SolidCAM as a milling tool. However, you can see that I have a problem with my UCS, so I'm going to mount this UCS to the coordinate system number 1. Okay, I'll say okay. So I have the model, I have the tool here back in my toolkit. Just take, drag, and drop it here. This particular small change in our diameter, instead of 32, it's showing 32.014. It's basically because of the STL tolerances. This you can easily change here to 32. And if I click on the preview of the tool, this is how my tool is going to look like. Fine. So my tool is done. This is tool number 6. Save and exit. And I'll go again to my machining file. I'll edit this toolpath. And I'll pick this tool that I just created. Okay, so I'll pick tool number 6 that I just created. Now if I click show, it shows me the tool. Accept this tool and hit the calculate button. I've got the tool and the tool path. If I run the solid verification here, you can see what it has done now. It has revolved the tool to show you how it would look when it is running on a milling machine. But the shape, everything is the same. So we take the tool, we take the profile and to revolve it, and it shows exactly how the machining will happen with that particular tool. Very, very important, because sometimes when you do a definition of the tool using simple parameters, you could end up missing certain features on the tool, which probably when revolved could generate collisions with your part. In such cases, you should have the tool exactly the way the manufacturer has manufactured the tool, and use this for simulation. So I can take it also into Solid Verify and run the simulation. So this is something very, very unique with our toolkit now. You can actually define the tool as it is, as the manufacturer intended, and generate the tool path. This is the same if I even take it into machine simulation. So if I take it into machine simulation, it's also the same. It'll show you the same tool, but again in the revolved condition on the machine, and you can run the simulation. Sorry. You can run the simulation on the machine with this tool. Perfect. Now, you would ask me, how would this run with a turning tool or a turning tool with the same tool table? So what I'm going to do is I'm going to open another file. We'll open a turning file. And I'm going to repeat the step again with the turning tool. And you can see that we can quickly grab in tools from so I'll open the drag and drop file, and I will also show you the drag and drop on this. Okay. So again, we are here into the toolkit. So I'm going to open the toolkit. I'll keep it open while I go back to my home page, and I'll go into the ISO turning. So I'm going to use maybe this one. Again, I'll use the PCL and R. In this case, we don't have to do a lot of work. So I'll use the first one. I'll click add to assembly. Now I'll get a message saying that I already have an assembly. Now, because I've not registered with this car, I can create only one assembly at a time. But if you're registered, you've created an account, you can create multiple assemblies. So I'm going to delete my earlier milling assembly and start off with my new turning assembly. So first thing I'm going to add is my holder to the tool. So I'll use the first one out here. I'll add this to the, pick this and add it to the assembly. And then the insert. Of course, I'm going to use, let's say, the CNMG. Insert, I'm going to pick the first one, and I will add that to the assembly. Okay, and quick, immediately, let's download the assembly. Go to save the file. Okay, let's go back to my downloads, cut this file. Let's go into my tools, webinar. I'll make new one here. Call this turning. Paste it. I'll say this is a turning tool. Okay. So let me open back SolidWorks again. Let's close this for a moment. Close this also for a moment, and then take the turning tool. So I have the tool here now with the holder and the insert as an assembly. Okay, let me save this. I don't need to do anything here because here the coordinate system is perfectly aligned. So I'll again open in SolidCAM my turning part. Go to the toolkit and I'll drop a profile insert here and minimize, go back to my assembly, maximize and import assembly from the CAD. Say OK. Here, instead of milling, I'm going to say generate this as a turning tool. Right, so we have it here. We have the turning tool, everything out here. Say OK. I'll just drag it and drop it into this. Tool number 10 is what I'm going to use. So I'm going to delete this toolpath or edit this. Edit this toolpath. Let's go to the tool and I'm going to select tool number 10 that we just created. So this is the tool. So done. Maybe change some things in the technology. I'll say 0.4 as my step over and calculate, run the simulation. If I go into the Solid Verify and start the simulation, you can see the tool, the holder, and the tool holder, everything coming up, the insert, the holder, as well as the tool holder. All of them have been brought in. Not only have been they brought into SolidCAM, you can also use them for simulation. Okay, so it's a very, very powerful tool table. So you can now imagine the possibilities are almost endless. You don't have to really waste or spend your time defining the tools. If you are already using tools from a manufacturer, from a standard manufacturer, and they're ready to supply to you the CAD files, you can just import it and start defining the tools as they are exactly into your files. Okay, so this is one of the biggest advantage that we have with our tool table. Another very important aspect here with the tool table, like I told you, is that we can define right angle heads as a component, as an assembly component, and we can program paths using those assemblies. So I'm going to open another part. Okay, let's go to the plain white background. So I have got a part here, and if I go into my toolkit and go into the definition or the view, you can see that I could take this CAD data from the manufacturer of the right angle head and use the CAD data as it is and mount my tool with a joint on this particular area here. Again, this is all mathematics, simple mathematics. You need to just specify your joint location point. You can also specify in this case, because this particular head also has got an axis here that can rotate from 0 to 90 degrees. So you can do any angle in that. So you can specify even what angle this head is, this particular subhead is going to be mounted at. Currently, it's mounted at 90. So you can mount it at 45. You can mount it at 0. You can mount it at any angle as specified by the manufacturer. So if I now run the simulation, let's go into the machine simulation. So I've taken this on a Haas. Okay, that's the first setup. Okay, so we have got let's go straight ahead. Now, because we are doing the tool optimization and using channel synchronization, so we are using the tools so that the tool change time is bare minimum. So you can have two paths mounted, and with the channel synchronization, you can then minimize the tool change time itself. So I would like to go straight away to the point where the right angle head is mounted. Okay, here it is. You can see that now the right angle head is mounted, and I can simulate this part using the right angle head from the CAD data that came to me from the manufacturer. And it's pretty simple to assign the right angle head onto the machine exactly the way we did, but slightly more steps than what we just saw while just pulling the data from a step file into our toolkit. So the fact here is that every component of this particular head is actually checked for collision. Okay, so if we go in, hopefully there should be some collision, because this particular coolant pipe runs into collisions, but we don't see them here, so we don't have it. But every single collision that is there, including a collision, if there is a coolant pipe, it's a metallic pipe, it's touching the part, you will get warning of the particular operation that it is it's colliding. So to show you even more in depth, I'm going to run this simulation here, the solid verify, and let's run it very slowly. Next one. Definitely we're going to have one collision somewhere. Okay, not on this side, maybe the other side. Okay, so whatever collision we have with the head, including the pipes, are immediately identified by SolidCAM. So what you have seen today is basically a very powerful toolkit, and you can import tools, whether it's turning tool or milling tool, from different manufacturers as a step file or a parasolid file, and take those components inside SolidCAM and create a tool out of it and use the tool as they are in programming your part. Okay, very, very powerful feature. The second feature that we saw was to take a right angle head and actually create programs using the right angle head on a 3-axis machine. So the output also will be according to the right angle head. Right, so let's move ahead, and since we are in one of these paths, I would like to show you also the drag and drop feature, which was earlier implemented with turning, with milling. It's now been implemented also in turning. So I can use the drag and drop feature to do turning straight away. So I have facing done here, and I have a template stored here for my turning. I can take this template and just drop it on the first and the last face, and the toolpath will be automatically generated for turning. Okay, so I'll click on my template, I'll drag, press Control, pick the first face and the last face, just leave the Control button, it'll ask the coordinate system, I'll accept the coordinate system, and my turning program is already created. So if I run this simulation now, and let's say even in the turning mode, we are going to have collision here, and this collision can be easily caught in Solid Verify. So you can see that we did have the collision here. Now, in order to avoid this collision, I can simply go into the toolpath. I can go into the modified geometry, and at the end extension, I'm just going to reduce it by -2 millimeters. So I'm going to stop it much before the chuck is there. Let's calculate, run the simulation, and we should be done. So no more collisions. So the drag and drop now works like a charm even on turning. So you can do turning, internal turning, grooving, all those things. Just drag the template and drop it on the geometry, and the toolpath is generated automatically. Fair enough. Let's move ahead. I'm not going to open the presentation, but I would like to go ahead with some of features that we introduced with SolidCAM. And let's open another part of the angular head. Okay, a very important feature that we introduced in 2021 was the roll-in approach for facing. Why is a roll-in approach needed? And this is needed because to avoid chip thinning that happens when you're using a straight approach or even an arc-based approach from the other side, you have chip thinning. In fact, Sandvik has got a very nice video on their website. If you just Google out roll-in approach on Sandvik, you can see that video, and they'll precisely show you what happens when you don't use roll-in and what happens when you use roll-in. You can see how the chip thinning happens when you don't use roll-in approach, and the chip thinning does not happen when you use the roll-in approach. So if I look at the face milling, what we have in the technology is that we have got a roll-in approach that's been provided now in 2021 version. So it's automatic. Just click on the roll-in version, hit the calculate button, and we have the toolpath. And if we run the simulation, we can see what happens here. The tool is entering, but not straight. It has got a roll-in approach. Okay, so it's taking a nice roll-in approach into the part, avoiding the chip thinning, and it's one way. So every pass that enters the material, it takes the roll-in approach. So this is a very, very important feature as far as the face milling operations are concerned. Again, this is done to enhance your tool life. Right, let's move on. Let's open another part. Let's go to the thread milling. In thread milling in 2021, we also introduced the fact that you can now give a multi-start thread in thread milling. So if I go into the operation, which was earlier simple thread milling, now if I go into the technology and into the advanced, we can now define the number of starts that are there in this thread. Okay, so just defining the number of starts, calculate the part, and if I run the simulation, we can see that it does. That's the first, the second start, again the first start, the second start, the first start, and so on. So it keeps doing both the starts. Start one first, then the next start, one more depth of cut with start one, then start two, again start one and start two as it goes, creating the depths into the part. So another very nice functionality that we introduced with our thread milling, we can now have multi-start threads, more than one. Pretty nice and very important. Okay, let's open another file to see what are the other enhancements that we have done with 2021. Go to 3-axis. Now, as a part of a 3-axis strategy, although we cannot really classically call it 3-axis, but it is part of 3-axis, we have released a feature called automatic 3+2. Automatic 3+2 functionality is a very unique functionality with SolidCAM, which helps you to generate toolpaths from different directions without the need for the user to define boundaries or from sides or from which side it has to come. Although in our Auto 3+2, we have got three different ways of defining the approaches. We have got automatic, we have got semi-automatic, and manual. In automatic, SolidCAM automatically finds out the best possible approach for machining any given part. Okay, the user did not define anything. In semi-automatic, the user or the software or SolidCAM expects the first major direction to be defined by the user, which normally happens to be the Z direction. Once that is done, SolidCAM then automatically finds the other possible directions of machining the part by itself. No need for any user intervention. And the third one, the approach that I've used for this particular part, because it's more or less a prismatic part and I know the directions, where the user defines himself different directions from where the part or the tool needs or tool can approach the part. By doing this, you reduce the time for SolidCAM to find the directions, but it completely eliminates the user input for A, the geometry, and B, the boundary, and C, the amount of stock that needs to be removed. All these things are automatically found out by SolidCAM. So this is what I'm going to do. I'm going to use a diameter 12 bullnose. I'll save this and I will calculate this toolpath. Now you ask me, of course, this is going to take about a minute and 15 seconds. You ask me, why did you do this automatic and why not, why did you do this manual and why not automatic? Like I said, this is prismatic. So the directions are very well known here, so I can define. But then the question comes immediately, automatic. Where do you use automatic? Once this part is calculated, I would like to show you a very complex part. And that is where automatic comes into play, because in that particular part, it is impossible for the user, or I wouldn't use the word impossible, that's a bit harsh, but it is going to be extremely difficult for the user to decide which all directions he needs to machine that part from. And once that kind of doubt creeps in, mistakes creep in, because fatigue, you don't know from which side it is going to machine. So you generate a toolpath from one side, run the solid simulation, check how much material is remaining, and then rotate the part manually to come to an acceptable direction, create another boundary there, machine from there. What generally happens with this is that you end up spending a lot of time in programming it. What could perhaps be done in like 30-40 minutes, you end up spending hours together. And B, there are a lot of mistakes that can creep in. Mistakes need not be always collisions. Mistake could always also be extra time taken to machine a part, unnecessary passes being generated in areas where there is really no material remaining. Okay, now all those things, all those guessworks are totally eliminated by the Auto 3+2. You can see that I defined 6 directions. Now if I run the simulation of this part, okay, let's run it quickly. So this is the main direction. And once this direction is done, it automatically flips to the next direction that I've defined. It finds the exact material, and I don't need to define any boundaries for this. It finds the exact material and the area to cut. Again, from this direction, the other direction, there's a collision with the arbor. Okay, I'll just say stop for this operation. And it machines also from the direction that I've specified, and that's it. I did not specify anything to this other than the directions that it needs to cut, because I use the manual method. Now you'll ask me, where do you use the normal method or the automatic method? So let me open a part. This is going to be just a quarter of the part that we have seen. So I'm going to open a part, and this part is called as a Pelton wheel, the most difficult part one can get to machine. So if I give this to a user and say, please, can you rough this out? Probably he'll get the first direction right, because it's going to be from Z direction. What after that? He'll say, okay, I'd like to go in this direction. Once these two directions are done, after that, the user is clueless. Unless and until he keeps looking for the simulation, keeps comparing the target, he will not get to know how and where this part needs to be cut from. Cut to SolidCAM Auto 3+2. I can just define this entire thing as one part. and ask it to automatically create the toolpath. So what you get here is basically this. So I have my stock here. I've just taken a quarter piece of the Pelton wheel, one segment of it, and we run. You can see automatically it decided that this is the best possible first approach. It was completely automatic. No manual directions have been set here. It completes this machining, finds out how much material is remaining, and based on the material remaining and the boundary that it automatically generates, it creates the area for machining. There, it automatically changed the direction. And I can also specify with Auto 3+2 what is the maximum limit my machine can tilt to. So I can say just go between 0 and 90, and it will only find the areas that are possible to be machined between 0 and 90. Anything more than that, it will just leave the material. Okay. So again, a very complex part done automatically by Auto 3+2. Right. Further enhancements with 2021. Let's look at more enhancements in the area of milling itself. So one of the most crucial aspects that we did in 2021 was introduction of a new finishing operation called as geodesic. Geodesic works unlike any other CAM system that you would have seen. Basically with geodesic, the spacing between the two toolpaths is always kept consistent, irrespective of whether it's a vertical wall, horizontal wall, or a intermediate wall, or any other feature. So let's say I have to machine an area between this particular curve, the pink curve that you're seeing. I want the tool to follow the area between this pink curve and machine everything in between, giving constant step over. Remember that there is a vertical wall here, almost a vertical wall. Of course, there's a small draft, but I would like to run my toolpaths on that. So let me calculate this toolpath. It's called as geodesic. What does basically geodesic mean? The dictionary meaning of geodesic is you have got a tub of water, you take a wire of a particular shape, drop it from top. The ripples that are created are basically mathematically they're called as geodesic ripples. So the distance between those ripples are always constant. And that's the same principle we are using here in geodesic machining. So you can look at this simple 3-axis, look at the wall, look at the fillet. Anywhere and everywhere, the step over is absolutely constant. It doesn't matter whether you're looking in this way or whether you're looking from top. The step over is consistent and it's equal. I've defined the step over of 0.3 here, and it's consistently 0.3 right from the start it approaches until the time it ends. So geodesic is very, very powerful in creating absolutely beautiful finishing toolpaths which have got the step over which is consistent. So if I've set 0.3, it'll be consistently 0.3 everywhere. It doesn't matter what kind of a geometry you're using. Right, let's quickly run over to another enhancements that we have done in 2021. Let's look at the boundaries. So in Turbo HSR, we have now developed a new system of generating boundaries. Now, this could be for any part. So if I go into my boundaries, I typically had the automatic boundaries. And if I use this automatic boundary and calculate the toolpath and simulate this, run the solid verification, you can see what happened here at the end. It doesn't go all the way down. It stops here because I've used the boundary condition as the center of the tool to be on the boundary. So anything below this will violate the boundary condition. So it stops there. In order to overcome this, we have got within our boundary something called as created automatically of the part sill out. So I can create automatic boundaries of the part sill out, and now we'll just calculate it. We've got completely different toolpath now. So let's run the simulation. Okay, let's use a ball nose instead of a, go to use a ball nose. Yeah, that one. Let's run the calculation and let's run the simulation now. You can see it's gone almost down to the final one. Okay. Now, if I use a different condition, instead of part sill out, I say tool contact. Okay. I'm not going to use part sill out, but I'm going to use tool contact. I'll have a completely different set of toolpath that will take care of that small region that was left over. So I'll go to solid verify, run the simulation, and you can see that it went all the way down up to here without the need to define any special boundary other than saying that use the tool contact boundary for roughing. We can also say part end height, and we'll give the offset value as 6. If I give the offset value as 6, then it will run around the entire part. Okay, so it's going to run around the entire part if I just provide the offset value out here. So this is something new that we introduced in 2021. All right, let's look at more features that we changed in or introduced in 2021, apart from, of course, the general features of tool table that we introduced. Open another part. With Turbo HSR, of course, we had this options already in HSR, but with Turbo HSR, we developed a new kind of combination toolpaths, and that is called combined constant Z with either linear or constant step over. So we have got a combination toolpath now, so I can define step over and step down and the shallow areas or angle, the slope angle, and calculate the toolpath. What you're seeing probably is a real-time calculation, and the part size is approximately about 180 by 150 by about 55. Issue with the audio, I guess. Okay, it's now connected. So with the With the linear machining, the angle for machining is automatically defined or derived by SolidCAM, and the user need not define these angles. So the angles depend on the geometries that are out here. So they're not the same. It again depends on the kind of geometry that it gets. Based on the geometry, it automatically changes the machining angle. Right. So this was about constant Z along with the constant step over. Jump a set of improvements that we did with SolidCAM 2021. Improvements that we did with HSS. So in HSS, earlier, if I had to machine these three faces, okay, I had to create three different tool paths. With 2021, I can now define multiple curves. So I can have, if I click on the curves, I can define one curve here, another curve here, and another curve here. I can have multiple curves, and I can have multiple faces, and it will just create a single tool path. Okay, so it will machine this face with parallel to this curve. It will machine this face parallel to this curve, and then it will machine this face parallel to that curve. So you can now define multiple curves in HSS. Keeping on the same area, or keeping on the same multiple curves area, since features of HSS are also taken into Sim5X, I would like to show you also how we take multiple curves and machine multiple surfaces in 4-axis. For example, I would like to machine this face here and another face down here, and this needs a single toolpath. This can be done where I just define, for example, here, two curves, one curve here and another curve here, and I just select two faces. And if I calculate this toolpath, you can see that it machines the first one, and then it retracts, travels to the other area, and machines the other face. So multiple faces now can be done in a single toolpath. You don't have to define multiple toolpaths to just machine, or we can't just define one toolpath for one face and then make another toolpath for another face. You can have multiple toolpaths as long as you're using the same tool in the same operation. Coming back again into our enhancements of Sim5-Axis, there are plenty here. Let me first close this file. I'm just going to close this file because every time this opens. Okay, so let me open Sim5X. A big change that we did was something that was asked to us by several of our users and customers worldwide, was a change in our rotary machining. So when you're machining rotary paths, in 2020 version, or even in 2019, when we did machine the rotary paths, the tool center was always in the center of the axis. Now, it's not a great idea, or it's not a great way of cutting, especially if you're using a bullnose tool and you want to cut where the tool axis and the rotary axis are almost aligned. That's not a great way of cutting, because when that happens, the center of the tool actually does not have any RPM, so it's not an efficient way of cutting. If you're using a bullnose tool or flattened mill, we have to, instead of cutting it right, or keeping the tool right at the center, we would like to offset the tool away from the part. And that particular offset is provided with a new version in 2021, where we call this as the side shift. So I can now provide a side shift of a particular value and hit the calculate button. It'll take about 30-40 seconds. This is so what for people who are looking at rotary machining, what rotary machining basically does is it uses a simple 3-axis roughing algorithm, but here, instead of cutting the part in a planar space, the part is sliced in cylindrical space. And then the toolpath is created on the cylindrical slice that it generates on the part. So it's basically a simple 3-axis roughing algorithm or simple 3-axis feature that's been implemented in cylindrical space. But the side shift is something that cannot be directly implemented on a cylindrical space. So side shift is a very complex algorithm that takes into account the tool geometry and then shifts the center of the tool away from the rotary center by the specified value, ensuring that the side of the tool always starts cutting the part. So if I run the simulation, let's go into the machine. That's much better visualized on the machine. So I'm going to go, let's say, to the right view. And you can see that once it starts cutting, okay, you can see when it's cutting, the center of the tool is away and it shifts because it's a bidirectional cutting. It shifts its direction as and how the direction changes. So the center of the tool is now offset from the center of the part. It's never on the center, exactly coinciding with the center. It looks very simple, but trust me, it's a very, very complex algorithm to shift this in just by defining a value. Right. More information about rotary machining can be found on several of our YouTube videos that are there on YouTube, on our videos on YouTube. Let's open more paths, more features. So we go to something very interesting that we released in 2021. Why I call this very interesting is a fact that I have customers, SolidCAM customers, who employ more than 40 to 50 unskilled laborers to actually do deburring of a part once the machining happens. Now, it's a very risky proposition because let's say you're cutting aluminum and you have machined the part is offloaded from the machine, sent to this manual labor to do the deburring. It all will depend on the mood of the laborer who is doing the deburring. Suppose if he has a very rough day, the pressure if he'll exert on the part is slightly more, you'll probably end up damaging the edge and generating a much bigger chamfer than what was required. So instead of doing an actual deburr, he'll actually provide a chamfer to the part is rejected. Also, you don't really get skilled people, they're very expensive. And most of the times, this deburring is done manually by people outside. So instead of doing that, SolidCAM now introduces an automatic deburring feature for CNC milling machines. It it's not that always the deburring is done by the manual labor, but it's also done on CNC. But the programming for deburring is probably the same. It'll take the same time as programming the part. Okay, that's one of the reasons why programmers hate to do deburring toolpaths on the part and they run a CNC machine. They let the manual operators do the deburring, or even when the operator has loaded the part and has got nothing to do, he just takes the part and starts deburring the part. Now all those days are gone, and we can now do the deburring automatically in 3-axis, 3 plus 5-axis minimum, and 4-axis and 5-axis. In all the 4 types we can do deburring. All we have to do in deburring here is I have to specify what is my target. So my target is simply the entire part. Okay, and I specify what tool. Currently with 2021, we support ball nose and lollipop cutters. Starting 2022 version, we'll also start supporting flattened mills to do the deburring. And that's it. We just have to specify what is going to be our deburring or what is going to be the chamfer width that we desire from this particular operation, and define what axis it is and simply hit the calculate button. It's going to take 15, let's say about 30, 35 seconds. But remember, that if I have to create the deburring toolpath for this, that could take easily an hour. Okay, so let's run the simulation. If I go into Solid Verify, I've got this part as coming out from the machining, and we can run the deburring. You can see that the edges are automatically found out. The holder geometry is taken into consideration so that there are no collisions, and it nicely does edge breaking of the component. No collisions even in corners where the tool cannot enter. Okay, so you can see that orange colored mark on the entire part just tells us the fact that this has been deburred. So whatever is possible is deburred. So if I zoom in, you can see that the chamfering has been done very nicely on this part. It took not more than 15-20 seconds to generate this toolpath. Now imagine the same part I would like to do now all in 5-axis. So I'm going to suppress this operation, and I'll move the 5-axis operation up, edit, and the only thing that I need to change here in the collision is, in the axis is, I'll just change it to 5-axis, and we calculate the toolpath. When you're using 5-axis, you can also specify what is going to be your tilt range. That means what is going to be your limit. You can put the limit between 0 and 75 degrees, like I've done here. So the tilting will happen only between this. I don't want it to go completely to 90 degrees. I want it to stay between 0 and 75 degrees. And the deburring will be done by keeping the part between these two angles only. Like I said, it takes approximately 35-40 seconds. Otherwise, this particular part, if you would like to deburr in 5-axis, I'm sure it's going to take 1 to 2 hours straight away. And then even then, you're not going to be sure whether it's going to do everything or not. Here, even the collision check is automatically done by SolidCAM. So if I run the simulation, whatever is possible, it's doing with 3-axis. What is not possible will then be done with 5-axis. There it goes. Now it's doing for this cylinder here, edge of the cylinder. Now it's going to do the outside of the cylinder. If it continued further, it would collide, so it changes the direction again automatically and does the, and now it's doing for the internal cutout. So all this tilting and collision checking is done automatically by SolidCAM. We don't have to bother or worry about it. You can see it's finding directions from where it can enter this part, so that it doesn't leave any of the edges unmachined. So it will try and machine everything that's possible. Linking again is done automatically by SolidCAM. No need for any manual intervention for linking. Since I've given it the limits, it's staying within the limits for machining this particular part. That's it. So it's completed this part in every possible side that it could find the edge and do the deburring of the entire part without any collisions, without any definitions from the user, everything automatically done and identified and machined. So it's a very interesting operation. that were introduced in 2021 version of SolidCAM. Again, it's available in 3-axis and as well as 5-axis options as far as the tool axes are concerned. Let's look at another very interesting thing that we released in 2021 was we enhanced our multi-axis machining to be able to detect undercuts when it's doing 5-axis machining. Generally, in our multi-axis machining, the toolpaths go parallel to the floor. Okay, so if I take a section here, sorry. If I take a section here, you can see that I have an undercut. So if the tool is going to go parallel to the floor, it's actually will not be able to machine this area at all. Let's look at the first toolpath where I ask the software not to machine the undercuts. So I'll calculate this toolpath. So you can look at the toolpath and you can see that obviously it cannot machine the undercuts. It has left the area unmachined. In the same toolpath, when I go into my toolpath parameters and in my sorting, I have asked the undercuts to be not to be machined. So I've got 3 options here. First one is not to machine the undercuts. Second one is to machine the undercuts. And the third one is to only machine the undercuts. So the second toolpath here that I have is machine only the undercuts. Now, when you have this option enabled, remember to use only a ball nose tool because the tilting happens only with a ball nose tool. So let me calculate this toolpath. It will identify and figure out only that area that has got undercuts and machine the area there. So let's look at the simulation. Let's run the simulation. So you can see that here I have also defined the holder. Okay. So it's also taking into account the holder. Not only did it tilt because of the undercut, but it also tilted more because of the holder that I've defined here. The last one is machine undercuts along with the toolpath. So you'll get the complete toolpath along with the undercut. So you can see that along with the straight toolpath, it's also gone into the undercut. So if I again run the simulation here, not solid verified, sorry. Okay. Going to use the host get, not the solid verify. So you can see as it comes closer to the undercut, it starts tilting. Ramp, and as it comes close to the undercut area, it will start tilting. That's it. So again, a very nice feature. Now, where do we apply such feature? So I'm going to show you a real world example on where this part is to be, or this particular operation is to be applied. Let's say I have a frame part, and in frame, you have got positive draft on one side and the other side automatically becomes negative, okay? So I have done my roughing, okay? So if I look at the updated stock, I've done my 3-axis roughing. Obviously, I'm going to have material left out here because 3-axis cannot detect this undercut. So now I would like to machine in 5-axis. I would like to rough in 5-axis only these areas where material has been left out, okay? And I want the software to automatically detect this. So what I did in my 5-axis multi-axis roughing is that I go into the toolpath parameters and I say just machine the undercuts and extend the area by 2 millimeters. So I'm going to save this. And let's calculate. Now, since this is a large part, it'll obviously take some time. Oops. That's because of here, my link. Use the ramp, Retract feed distance, use ramp. Oops, what is the problem? That's strange. Did I use, okay. I'm so sorry. Let's look at the floor faces. Okay, so sorry. I need to define all the floor. My bad. So what it is going to do now is it's going to detect all those areas where the previous tool did not enter, or because of the undercut, the previous tool did not enter. And only those areas, it is going to generate the roughing program. You can see what it did very nicely. It just detected areas where the previous tool did not enter, and it will machine only those areas where the previous tool could not enter because of an undercut. So if I run the simulation, let's go to Solid Verify. Okay, let's run only on one side here. And you can see it's doing nice 5-axis roughing. Automatically, it'll take step over based on the material that is remaining, and it will do the machining of it. No. Again, this is full 5-axis. So very interesting features have been released by SolidCAM in 2021 version, which includes like what we saw, edge breaking. We saw this automatic detection of undercuts and machining or roughing of undercuts using automatic detection. Apart from this, we have also released another very important feature in SolidCAM's 5-axis kitty. I think after this, I'm just going to show you the new simulator, and then we'll wrap up. So I'm going to use what we call as the edge trimming. Now, what happens with edge trimming? Why is this released? Several of our customers manufacture parts for aerospace using composite materials. And several of our customers are also into the automotive domain, and they manufacture parts using vacuum forming process. In both these processes, you need to trim the part to the final shape. And sometimes the parts are not simple, they are pretty complex, and you need to use either 4-axis or 5-axis machines to complete this trimming. So once this edge is known, the user then needs to create the toolpath, and the toolpath has to be created in such a way that it actually trims the part. In edge trimming, this is automatically done by SolidCAM. It identifies the edges, and once the edge is identified, it then creates the trimming toolpath in 3-axis, in 4-axis, as well as in 5-axis. So you have got all the options out here, 3, 4+1, that is auto tilt, and 5. So we're using 5 here, and you can see that the edge detection is automatic. Calculate this toolpath. Done. It's pretty quick, so it doesn't take much time. And we show you the simulation. So this is how it will trim both the pockets and this particular area here. So it will trim off the excess material and it will generate the final shape. Very important for people who are doing composite materials, and also for people who are into vacuum forming. Right, let's quickly go to our new simulator, and let's open again the part that I just generated for my rotary, and I'll right click on this on the operation here, and I'll go into the new SolidCAM simulator. You can see the new SolidCAM simulator is a floating window. I can make it as a floating window, or I could just merge it with the SolidWorks window that I have. Or I could just drag it and put it into another monitor and continue looking at the simulator while I keep working on my part. Very, very important. Okay, so you've got several options here where I can see the toolpath while the machining is happening, or I could switch off the toolpath, uh, or I can follow the tool, or I need not follow the tool. I can show the material removal or just a plain simulation. I can also record the simulation. Now this is slight, it will slow down your system slightly, but I can select this record simulation. And by doing that, it will allow you to go back and forth. When you go back, it will add material. When you go ahead, it will remove material. So you can always go back and forth to see if you have missed anything, because it was working on another window and you just missed to see certain things. So you can go back, it will add material, and then it will start generating the simulation again. But again, like I said, it's going to be a bit slow when it comes to recording and then playing it. So what you're seeing here is a toolpath as well as the cutting simulation of the part. So I can switch off the toolpath. So I'll just see only the cutting simulation in this case. For people who would like to have different themes, I can stop it and I can change the theme. I can go into what we call as the solid verify kind of theme, where I can do even a comparison between the actual part and the machine stock. Okay, so I can stop here and I can run the comparison. So it shows me basically between using colors, it will show me the amount of material left out. So it here says that it's more than 1 millimeter anyway. So I can drag this and I get a completely different set of a color. So in the comparison state itself, I can start running the simulation. So you can do comparison as well as you can switch off the comparison and only run the simulation out here. There is a complete webinar done by Anthony Calderon on the new simulator. It's available on our website. It's also there on YouTube. You can go and have a look at it on what are the complete features of our new simulator. This particular webinar was more intended to just give you a glimpse of what all new things that we have with SolidCAM 2021. And we urge you to go on to the new version to take the advantage of the new features that we released with 2021, especially features like edge breaking, geodesic, the new tool table, the new simulator, enhancements in 3D HSR and HSM. Also in finishing, we saw geodesic 2.5D like the roll-in approach, thread milling where we did multi-start. We have multi-start thread capabilities now. All these features we would like you to take advantage of by moving to the latest version. So if you have any questions or if you want to ask me anything, the question bar is open. You can also write to me at on my email address. I'm just going to put my email address here. Just a moment. I'm going to my chat area. So if you have any questions, you can ask me questions and I'll be more than glad to answer. I think there is a question that has come from Andre. Andre wants to know when assemblies of turning tool are correctly visualized in Solid Simulator. I think they are, Andre, with the new release of 2021 SP3 HF1. I don't know if there is something else other than what we are seeing now that you have seen and you would like to ask. In that case, you could always write to me an email and I'll be more than glad to answer you. Because right now with this just a single sentence, I'm not able to visualize what exact problem do you have in visualizing the turning tool, especially the grooving tool inside SolidCAM simulator. Right, if there are no more questions, it was really nice presenting to you the new features of 2021. I hope you have liked it. It was about 90 minutes. I hope it was not long. If you would like us to do a one-to-one webinar or one-to-one presentation, okay, somebody's asking me for my email, so I'm just going to put one slide at the end. Okay, just give me a moment because I could not put on the chat. Okay, just a moment. Okay, so that's my email. Going to change the font. Get it back here. So that's my email. Right, so if there are no more questions or you would like us to come to your place or you'd like to have a one-on-one session on what's new, we would be more than glad to offer you this session via either Zoom or GoToMeeting or GoToWebinar using one of these tools or even Microsoft Teams. And we can do it one-on-one for you so that you can ask your targeted questions to us and we will be more than happy to answer them. Right, so if there are no more questions, I see that there are no more questions. If there are no more questions, thank you very much for attending the webinar. I hope you liked it. If you have any suggestions, comments, questions, please write to us on the email that I just provided on the screen. I'll be more than glad to answer it. Thank you very much. Have a nice day, have a nice evening, and take care, stay safe, bye-bye.